First of all, I wish to thank Daniele, Karin, and Julie for this last minute invitation, because I just asked to participate very late after the program was already done. So this is a very good occasion for me to present our recent results on unconventional computing. Actually, we work more at the device level. So actually, I will discuss about some building block that can be used for unconventional computing. I wish also to thank the funding agency. We have different funding agency, one also from China and Italian Space Agency, because Spintronic is really interesting for space application because it's radiation address. So let's start to show you where Messina is. I think most of you already knows we are in the top right corner of Sicily. And this is the view of our university. So every day, basically, this is the new building we have in the Faculty of Engineering. And this is the group which works in Spintronics in Messina. Actually, we have 3 permanent people. Now Mario is professor in Polytechnic of Bari, 5 postdoc, and one PhD student. So we have also position for postdoc. If someone is interested, we can discuss later. So this is the outline of my talk. I wish to start from the switching of a single ferromagnet. This concept has been introduced several years ago by a milestone paper by Mihai Miron that basically launched the Spintronics. In this paper, they studied multi-layer platinum, cobalt, aluminum oxide, as the dynamics of this ferromagnetic layer responds as a function of an applied current which flows in the platinum. And thanks basically to spin-orbit torques, they found out rich behavior. In particular, they were able to say that below a certain critical current, actually there is no change with the regular switching. So they apply a field which is close to the coercive field. Then there is a second region here where basically you see that the current reduces the field that you need to apply to switch the magnets. And there exists a region, which is basically this region here. Basically, the switching is driven by the current pulse. So we have studied in terms of micromagnetic modeling this system. So first of all, we have reproduced the behavior of the device as a function of the auto-plane field. And then what we did is to predict how this system works in presence of an in-plane field, which is applied along the direction of the current flow. So actually, we are going to study current pulses, which are limited in time because we are interested in something which is low energy consumption. In particular, we fix our time duration in 10 nanoseconds. And the results of this study was a phase diagram where we can identify 3 different types of switching. So actually, the first one is a direct switching, which is basically occur in this region. The second one was a switching via an intermediate state, which can be found here. And then there was a stochastic switching. So basically a low field and for almost any current which is applied. So let's start with the first one. So actually we apply field larger than 10 millitesla and a current pulse. And what we see is that you can see the switching that occur, and it goes from a positive value of magnetization to a negative value. Here the value is not really -1 or +1 because we are simulating 300K, so we are adding temperature. So in the average, the magnetization fluctuates around this number, this value. And just to show you how the switching occurs, so actually, we apply the current pulse. This is the positive state. You see the temperature give fluctuation. Basically, the switching is not uniform. So actually, you have, depending on the seed of the simulations, you can have nucleation of bubble or multiple bubble. Then this bubble grown up in the system up to its collapse at the other side. And this mechanism of direct switching is thermally assisted, activated, in the sense that if we reduce the thermal fluctuation, actually for the same current, you can also get the switching. For example, if we consider a current pulse of 1 times 10 to the 8, actually we have the switching at room temperature, but below 200K, actually the switching does not occur anymore. So it's thermally activated. The second region of the phase diagram is the switching via these intermediate states. So actually, here you get a different behavior. So actually, we apply a current pulse, and before to switch the current, actually the state is fixed along in a strong non-uniform configuration. As you can see here, you have several bubbles. 5 times 500. 500 times 500 is the same device of the experiment, so the same sites. Once you remove the current, so the pulse is switched off, actually this state relaxed to a uniform state. As you can see, the state is basically characterized by a bias with a component of the magnetization, zero component of magnetization, which is smaller than 0. So it means that the area of the bubble or this solid, these states are larger than the ground states. So actually, this is really interesting because you can really drive switching using a metastable state. So now, when we go at low field, so what we found out is that for some current, of course, you don't switch the current, you don't switch the state, so you need a critical threshold to overcome a critical threshold to get the switching. And what the system does is it goes toward zero average magnetization, which is basically a complex magnetization pattern. And once you switch it off the current, it can move in a random way to positive or negative value. As there are some configurations which are very long, are metastable state with very long relaxation time. So actually, this, for example, can be a starting point to think on how to use the system as a random bit generator. And actually, what we have done starting from this point it was a systematic and massive study in terms of simulation to find out which should be the best configuration. In particular, we tried to study also all the possible applications that this type of system can have. And at that time, it came out a paper which basically identified the possibility to use this intermediate state as a clocking state for nanologic. So in particular, for people that are not familiar with nanologic, so we have a tantalum layer in this experiment. So you can put several ferromagnets. One is less sensitive to the current and can be used as a reference layer. So you apply current pulse. You drive intermediate ferromagnet at non-uniform configuration or something which is basically as an in-plane configuration as told in this paper. And then when you remove the current, because of the deeper interaction, you can basically drive this information in the site. And just before to study, of course, this type of behavior, you need to characterize the clocking behavior here. And these particular devices, they found out that you have no really 50% probability to go in up and down system because of some defect and so on. So they, in this case, they get 40 and 60, which is the best they measured. And of course, this is interesting because you have a lot of application for nanologic. You can design very complex three-dimensional full ladder, and also you can use implementation quantum dot cellular atom as proposed here. And the advantage of this is that there is a better routing, so you can transfer information where you want without transferring charge. Also, the state is stable, so can be basically stay also when you switch it off the power. It's radiation hardness, so can be used in space. And ideally, it's low power dissipation, depending, of course, on the current pulse you are applying. And this can be used for energy harvest computers, so actually batteryless computers. So you can basically intrinsically have the state always at the same state when you have no energy from the ground, from the external source. All right, so what we've done in this direction is basically we studied all the clocking properties of the system, and actually this is the reference system. So it's basically the current is applied in this direction. You can read the state via this the voltage in these two terminals. And what came out is that actually the clocking state is not uniform, but is occur with the nucleation of some domains. In particular, here we have no DMI. And as you can see, actually you apply current pulse, you get some, you stabilize a domain, a Bloch type domains, which are well ordered in space. The periodicity depends on the magnetic parameters. And when you indeed at DMI, actually, you together with this non-uniform state, you can be able to find out some unstable region of behavior. So basically, here the different intermediate states is basically a nil domain wall. Here, we'll discuss later why this mechanism. And also you can find some regional parameter where basically you go to the clocking state, you can go to positive or negative value of the magnetization. So unstable in the sense that the energy with the barrier energy between the free states is basically not so high to maintain the metastable state or to maintain one of the two uniform states. So the question is why we have these two different types of behavior. So the answer is pretty simple, because without DMI, actually you try to stabilize block type domain configuration. So this is what you're doing here. Instead, with DMI, actually you stabilize nil configuration. So this is basically, if we compute the energy and compare the energy of the states in the two different systems, actually this is the minimum here, this is the minimum here. So how we can take all this information in order to design a random bit generator? Actually, what we have done is look into literature. Actually, one of the first proposals of random bit generator was come out from this Japanese group. Actually, they studied, they worked near the probability of 5% to 50% to get switching. So they apply current pulse. They work at this bias point. And then depending on which state you get, which can be 50% up or down, they create the random bit. Another proposal was done by, we presented this paper in a collaboration from Japanese Gordier group. Actually, they used the stochastic superparamagnetic tunnel junction in order to create random bits. And this, basically, you have, this approach basically were tested with the nearest procedure, I think, and overcome this process, the procedure, the tests. And also there was a proposal by Roy group where basically they take advantage of a free terminal devices, that what we are looking for now. And actually, in the very simple scenario they studied here, because you have the energy landscape, which is a quartic potential, actually the current can modify the stability of this point from unstable to stable. Then you apply current, the system move in this point, you remove the current, then you have a 50% probability to go on the left, on the right. Actually, in the system, they just make 10 trials, so actually it's not really massive check if this system works or not. So, so actually, we continue to study the same system, and we designed the experiment in collaboration with Professor Takahiro Moriyama. So the system we have at the end we figure out is we need large spinol angle, so we use tungsten because it has a spinol angle of 0.3, around 0.3. Then we have the ferromagnet, which should be large enough in order to avoid the effect of pinning site, but should not be that large in order to avoid any correlation between nucleation in different sites. This is, for example, we studied a 1 micrometer diameter dot here, and this is the SEM image of the device, and this is actually the experiments. So we apply current pulse, and here you can see that depending on the pulse, you can get dark or white color, which correspond to positive and negative bit. So we did really millions and millions of trials in order to have very good statistics with the samples. And actually, this is a summary of the experimental results. What is interesting is that this type of system of device is very sensitive to the angle of the field of the applied field. Actually, because when you apply current pulse, you have a Wörster field. You have also field like torque. You need a bias field to bring the probability to get 0 and 1 50%. So actually, the plane field is not enough. You need to tune also a small tilting angle because of the some bias which come from the Wörster field. And the behavior of the system is very sensitive to this tilting angle. In particular, at this theta angle, we get almost 50% for switching down to up to down, down to down, and up to up. So we make all the 4 different trials. So in micromagnetic simulation, actually, this is an example. In this particular system, we are able to drive the system in a uniform state. So actually, this is unstable in the case of without current, but becomes stable with current. Actually, once you remove the current, so you can see that at some point the system goes in a very complex scenario, and actually will relax randomly toward one or the other direction. The simulation has been done by Mario Carpentieri. So actually, this is a summary. So you can see here, simulation also predict possibility to jump from down to up to down, down to down, and up to up. It's a summary of the experimental results and micromagnetic results. Actually, you see that this is the best probability here in the experiments. And actually, if we want to just consider the number of bits which have 0 or 1, you can see that you design the population of the bits. Actually, you can see that there is the curve across the 50% probability at some point. But we are near. Actually, in this point, we check mathematically that this is still a random bit generator with the property to define it. So the advantage of this system is that basically we have a random bit on demand. So actually, when we want random bit, we can create them. So we are not dealing with any probabilistic process. So actually, just we apply a current pulse, and then we read the random bit. Actually, we can use multiple of these dots. Actually, we have 4 dots. We already an experiment of 4 dots which work very well. And then you can create multiple bits at the same time. Here you have to have a larger distance. But you can also apply a current in this direction. Then you create a random bit here. And then you can use it using clocking to here to move the bits where you need. So actually, instead to use the clocking in this direction, actually, you can use clocking in each of these channels to move the information. And we have saw that in this way, you can save more energy because the pulses are smaller. Instead, when you apply current in this direction, actually, the length of the pulses is much larger if you sum all. Finally, I wish to show our very recent results on antiferromagnetic dynamics. So the motivation is that there are more antiferromagnets than ferromagnets, and you have a lot of options. And actually, there is an intense research now on this direction, and this can be, as been already demonstrated, can be used with sensors. They can interact with superconductivity, and also in Spintronics. In particular, they were the first application of antiferromagnet was the stabilization of reference layer in MTJ. But also antiferromagnets were used to demonstrate very high velocity of domain walls. And there is now a lot of research effort toward the development of antiferromagnetic spintronics. For we're interested, there are a few reviews here. And also skyrmion can be stabilized in antiferromagnet. And actually, you remove the problem of the spinol angle. But also, has been proposed in several papers, the possibility to use also antiferromagnets as terahertz generator, spin terahertz generators. The question is, we can use this for neuromorphic applications. Actually, there was this experiment which showed that memory state behavior in some antiferromagnets. So this can be, for example, used as memristor. Also, there was a proposal by a Slavin group showing that in some configuration, this oscillator can create some pulses. And actually, we are investigating this behavior in collaboration still with Andrei Slavin. And the application of this type of device is basically in a spiking neural network. So this can be a building block of these networks. Actually, this simulation, the study has been done mainly by Vito. We are able to tune the polarization of the spin current by properly tuning the current which flow from this two terminal and this two terminal. So a combination, we can have polarization which is collinear to the reference layer, which is perpendicular, which is also can be at any angle. For example, here has been investigated this collinear configuration. A Slavin group studied this perpendicular configuration. So we have studied basically all the possible directions. And the model that we have implemented actually is a continuous model. So we consider a discretization cell, and we define two vectors for each cell, one which is basically the average of all the atoms which point to one direction, and the other one which is the average of all the atoms which point in the opposite direction. And we use two Landau-Lifshitz-Gilbert equation to describe this dynamics. And actually, I wish to spend just a few words about the exchange interaction. So actually here we are dealing with at least two types of exchange interaction. Non-homogeneous exchange interaction, which occur inside the same discretization cell here. So it's proportional to the magnetization of the other sublattice. But also we have the interaction between parallel magnetization between two adjacent cells, and also the interaction between anti-parallel magnetization. So you have here at least three different exchange interaction. We have checked this with some atomistic computation. Actually, simulation reproduce pretty well the behavior when we derive the parameter from atomistic stuff. So now I wish to summarize most of the micromagnetic simulation. Just I will focus on three different configurations, which are the more simple to realize experimentally. And actually, the first result is that we have, so actually here we don't have any DMI. So actually, the first result is that we have subcritical Hopf bifurcation. So it means the critical current to switch on the dynamics is larger than the critical current to switch off. So see, if you start from static state, you need a larger current to excite, and then you can reduce this current and work inside this hysteresis region. And this hysteresis depends on this the initial angle between the polarization and the equilibrium state. In particular, is larger as the field, the spin polarization tend to be at 90 degrees. So as you can see from this device. And actually, this can be, for example, used for neuromorphic. Also, just for your knowledge, the frequencies does not really depend, at least just above the critical threshold, does not depend on this type of polarization. So it's an intrinsic property of the system. And we did a systematic study as a function of parameter, damping, thickness, exchange constant, and basically we studied the hysteresis. The only thing I wish to say is that for large damping, seems that these hysteresis disappear. So if you have very large damping system, actually you don't get any more you move from subcritical Hopf bifurcation to supercritical Hopf bifurcation. And in an interesting way, if we study the ground state as a function of the DMI, actually, what we see is that there is a transition from uniform one to a non-uniform one. In particular here, the ground state is the nil domain configuration. And what is interesting is that the DMI also remove this hysteretic behavior, and in particular, already at 0.5, you have basically that switch on and switch off current collapse. Of course, because here you need to start to make a rotation of the sublattices, but here basically you have domains, so you just need to move them. And the frequency also are not really sensitive to this DMI parameter. And what we found out very of interest is that actually when you remove this hysteretic behavior at the threshold, you can excite very strong nonlinear dynamics, which is characterized by basically you start to nucleate a domain in one side, and it is pushed slowly, as you can see here, red curve, to cover the whole device, and then it's pushed very fast. So actually, it's like you charge a little bit you charge this domain to go to have both side in this lateral configuration. There at some point it go out very quickly because of the current which push out this. And actually, if you remove the current before this pushing out, it come back. So actually, you have no you don't get any signal like this. So just to show the difference between what has been done has been proposed by Slavin and what we have done here, actually they fix a bias point inside this hysteresis region, and they need an additional AC field, AC current to create spikes. Actually here, we're just applying a DC current, and after some time, which we can tune actually, you create a spike. So actually you need just a bias current instead than a combinational tune. All right. And of course, the DMI play an important role here. If you are interested in more details, actually you can look to this, our recent archive paper. Just I bring out the conclusion, and that if we combine spinol with ferromagnet or antiferromagnet, we can create random bit generator. We can use an efficient way to transfer information. And also we basically can create combo generator for neural networks, for spiking neural networks that can be created within an antiferromagnetic spin torque oscillator. Thank you very much for your attention. I wish just to advertise a conference we have on July in Italy, in Puglia. So if someone is interested, still in the next weeks, there will be open the submission of the abstract. Yeah. Thank you very much for your attention.